G'day. Today we're going to start our first lesson in our factoring unit. You may ask yourself, why are we learning to factor? Factoring is a step that we will have to have next chapter when we are studying quadratics. Algebra is about graphing and interpreting graphs and figuring out how they work and how to read them. And some graphs are graphed as parabolas, which uses a quadratic equation. And to solve them, you have to be able to factor. So our first lesson on factor, we're going to back up and kind of start factoring some things that you've learned in previous years. And we're going to build on that because today our final goal is to factor monomials. And to factor monomials, you have to have a little background on it. So this may be review, but we're just going to back up here. First of all, prime factorization of numbers. If you think of prime factorization and what those two words mean, prime is a number that is only divisible by itself and 1. Factors are numbers that multiply together to get a product. So when we say prime factorization, we are finding prime numbers that multiply together to get a number. Now, in younger classes, you probably used the tree method, where you would do something that looks like this. This might look familiar to you. Sorry, that's 5 times 5. We're going to use the ladder method. I like this method better. It works faster. I can find the prime factors together in a matter of seconds, and all the prime factors are lined up very nicely. So you can use this method if it works for you. But prime factorization of a number, what you do is you have to know what the prime numbers are. And I'm just going to write them up here. 2 is the smallest prime number, then 3, then 5, then 7, 11, 13, and the list keeps going and going, but I'm just writing the first prime numbers that we know. So what we're going to do to find the prime factorization with the ladder method is we always start with the smallest prime number 2, and we ask ourselves, is 50 divisible by 2? If the answer is yes, we divide it by 2, and that would be 25. With the next 25, again, we start with the smallest prime number, which is 2, and we ask ourselves, is it divisible by 2? It is not, because it is not an even number. The last number does not end in 0, 2, 4, 6, or 8. We go to the next prime number. Is it divisible by 3? I don't know if you learned divisibility rules or not, but to determine if a number is divisible by 3, we find something called the digital root, which means we add the digits together. We add 2 plus 5. That equals 7. And we ask ourselves, is 7 divisible by 3? It is not. So the number 25 is not divisible by 3. We go to the next prime number, which is 5. And of course, 25 is divisible by 5. And 25 divided by 5 is 5, which is a prime number. So now we have right here, located very nicely on the side of the ladder, excuse me, are all the prime numbers, prime factors that multiply together to get 50. 2 times 5 is 10, 10 times 5 is 50. So we would say the prime factorization is 2 times 5 squared. Now we're going to use this in just a minute to find greatest common factor of 2 numbers. But I just wanted to spend a little time getting you used to this method of finding the prime factorization of a number in case you need this to find greatest common factor. Just a little more practice here with the same thing. Okay, remember our prime numbers 2, 3, 5, 7, 11, 13, and so forth. Always start with the smallest one, which is 2. Is 76 divisible by 2? It is. 76 divided by 2 is 38. Then you start over again with the prime number list. Is 38 divisible by 2? It is. That would be 19. And what we know about 19 is that it is a prime number. So the prime factorization for 76 would be 2 times 2 times 19. Or if we wrote it in exponential form, it would be 2 squared times 19. Same thing, we're just going to practice the skill a little bit. Is 124 divisible by 2? Yes, it is. That would leave 62. Is 62 divisible by 2? Yes. That happens to be 31, which is a prime number. So 2 times 2 times 31 are all prime numbers, and the factors multiply together to get 124. So the prime factorization of 124 is 2 squared times 31. Now we can use this to find greatest common factor of two numbers. Now, when the numbers are small enough, you can probably mentally look up there and figure out the greatest common factor for 24 and 60. When the numbers get larger, it's going to be a little more difficult, and you need a method to figure it out if you can't do it mentally. So if you looked up at 24 and 60 and were to guess what you think the greatest common factor is, I don't know what you would guess, but we're going to figure it out, show you a method in case you do not know how to do that. We're going to find the prime factorization for both numbers first. So 24 is divisible by 2, that is 12. 12 is divisible by 2, that is 6. 6 is divisible by 2, that is 3. Now we know the 2 times 2 times 2 times 3 is 24. So there's the prime numbers, the prime factors that make 24. 60 is divisible by 2. 30 is divisible by 2. It is not, 15 is not divisible by 2, but the next prime number is 3. It is divisible by 3. 5 is prime. Now, once you find the prime numbers, you look for numbers they share. They share a 2, so I write it down. They share another 2, so I write it down. They share a 3, so I write it down, and I'm going to multiply all of the factors that they share. 2 times 2 times 3 happens to be, and here's, I had it written out a little differently. I have these written horizontally instead of vertically, but again, it shows you that they share a 2 and a 2 and a 3, and so the greatest common factor for 24 and 60 is 12. So this is just a method we can use if you can't look at them. Now 56 and 140, if I ask you what the greatest common factor for those two numbers are, this one's a little harder because the numbers are bigger. So we can figure it out pretty quickly by using this method. 56 is divisible by 2 because it is an even number. That would be 28. 28 is divisible by 2, 14, which is 2 times 7. So 2 times 2 times 2 times 7 would be 56. Let's do 140. It is divisible by 2. 70 is divisible by 2. Now when we get to 35, that is not even, so it's not divisible by 2. If I find the digital root and add 3 plus 5, that is 8. 8 is not divisible by 3, so that means 35 is not divisible by 3. The next prime number is 5. 5 times 7. What do they share? They share a 2, a 2, and a 7. So 2 times 2 times 7 would give us the greatest common factor for 56 and 140. Here I have the same prime numbers written horizontally, showing that they share a 2, a 2, and a 7. When you multiply 2 times 2 times 7, of course you get 28. If you were to guess the greatest common factor for 225 and 195, not sure what you would guess, but again, these are larger numbers, so they're a little more difficult. But we can use this method for larger numbers. 225 is not even, so it's not divisible by 2. 2 plus 2 is 4. 4 plus 5 is 9. It is divisible by 3 because 9 is divisible by 3. So when I divide it by 3, 21 divided by 3 is 7. 7 times 3 is 21. So I had 22 minus 21 with a remainder of 1. That's 15 divided by 3 is 5. I kind of did a shorthand long division there. You can use your calculator with that as well. Is 75 divisible by 2? No. Is it divisible by 3? Well, 7 plus 5 is 12, and 1 plus 2 equals 3. So yes, it is divisible by 3. It happens to be 3/4, 75 cents. And then we have 5 times 5. For 195, is 195 even? No, it is not divisible by 2. Is it divisible by 3? Well, 1 plus 9 is 10. 10 plus 5 is 15. So we have the number 15. We add them together and there's 6. 6 is divisible by 3, so we know this is divisible by 3. 19 divided by 3 is 6, which would be 18 with a remainder of 1. Now we have 15 divided by 3, which is 5. 65 is not even, not divisible by 2. If you add the digits together, that would be 11, and 1 plus 1 is 2, not divisible by 3. So we're going to do 5. 6 divided by 5 is 1, with a remainder of 1, and 15 divided by 5 is 3. 3 times 5 times 13. What do they share? Here they are written out horizontally. They share a 3, they share a 5, so the greatest common factor is 15. So this is a method that if it helps you, you can find the greatest common factor of numbers. We can use the same method when finding the greatest common factor for 3 numbers. If we were to do this for these 3, 18 is divisible by 2. 3 times 3. 36 is divisible by 2. That would be 18. Divisible by 2. 9 divisible by 3. There's the prime factorization for 36. For 54, divisible by 2. If you need to do your long division, 5 divided by 2 is 2, which leaves a remainder of 1. 14 divided by 2 is 27. So we divide by 3, a 9, a 3, and a 3. So I can really quickly look up here. Here they are written out the same way, but vertically. They share a 2 and 2 3s. So 2 times 3 times 3, greatest common factor would be 18. This is all, again, background so that we can get to where we're going to start finding the greatest common factor for 2 monomials, which is where we're at now. So let's see how this is really going to work. We're going to take each monomial, and we want to get to the point where we can look up here and try to do this mentally and pull out the greatest common factor. But just to show you how it works, for 3x cubed, if I was going to write out the prime factorization for that, I would first do the prime factorization for 3. Well, 3 happens to be prime, so I just write 3. Then what multiplies together to get x cubed is x times x times x. So there is the prime factorization for 3x cubed. For 6x squared, 6 is not prime, but we know 2 times 3 is 6, and those are both prime. And then we have 2 x's. So all I've done here is write out the prime factorization for those 2 monomials. Now, what do they share? We're doing the same thing. They share a 3, an x, and an x. So 3 times x would give us the greatest common factor, which is 3x squared. So if you were doing this mentally, you would look up here at the 3 and the 6 and say, what's the greatest common factor for 3 and 6? Hopefully you would know that is 3. And what you do is you look for the variables. They have to look for variables they share and then take the lowest exponent, because if they share x's and one has 3 and one has 2, they share the lower number. They can't share the higher number. So I would look up here and say the greatest common factor for 3 and 6 is 3, and I'll take the x squared because they both share 2 x's, 3x squared. So we do want to try to get to the point where we're doing this mentally. We're just showing you how this works. So on this next one, okay, look at 4x squared and 5y cubed. We want to think about what do they share, what would be the greatest common factor for this pair. 4 is not prime, but 2 times 2 is the prime factorization for it, and then we have x times x. 5 is prime, so we have 5, and then we have y times y times y. Now I wrote it here where I would stack things that they share. Notice that nothing is stacked. They don't share any of these things that we wrote out here. So the question would be, what is the greatest common factor if they don't share anything? Well, if you go back to the numbers 4 and 5, factors of 1 times 4 equal 4, and factors of 1 times 5 equal 5, and so they actually share a 1. So if you do all of this and they do not share anything, they do share the common factor of 1. You just don't see it there. You just have to understand that that is true. This one has one that's negative, so let's think about this, what it would look like. 15 is not prime, but the prime factorization for 50 would be 3 times 5. So we have, oops, I didn't write out the steps here. 3 times 5 times y times y times y. That is our 15y cubed. When we have a negative number, we're going to factor out a negative 1. When you factor out the negative 1, you're left with 20y. 20 is not prime, but if we find the prime numbers for it, it would be 2 times 2 times 5. and then there's 1y. So what do they share? They do not share the negative 1. So our final answer is not going to be negative because they don't share the negative 1. They do share a 5, and they share a y. So our greatest common factor would be 5y. If you're doing that mentally, you look up here. Don't worry about the negative, and you know that the greatest common factor of 15 and 20 is 5. You look for the variables. They share a y, and you take the one with the smallest exponent, so it would be 5y. 6x squared and 5x squared. Take a moment to look at that and see if you think you could figure out the greatest common factor for that pair. For 6 and 5, 6 we have 2 times 3, and for 5 we have 5. They do not share any common factors other than 1. And then they both have x squared. They share the x squared, so the greatest common factor would simply be, my slides here, x squared. Now, how do we use greatest common factor in the real world? Here's an example. Garrison is creating a web page that offers electronic greeting cards. He has 24 special occasion designs and 42 birthday designs. Cards will be displayed with the same number of designs in each row. This right here is a little clue that you're going to be wanting to find the greatest common factor because you want the same number of designs. Special occasion and birthday designs will not appear in the same row. How many rows will there be if Gus puts the greatest number of designs in each row? Again, here's some clue words. The greatest number of designs in each row means we're looking for greatest common factor. So we have the numbers 24 and 42. Maybe you can look at those two numbers and know what the greatest common factor would be. If you do not, you need a method to figure it out. So if I use my little ladder technique here, you can see that 2 times 2 times 2 times 3 equals 24. 42 divided by 2 is 21. 21 divided by 3 is 7. What do they share? They share a 2 and a 3. 2 times 3 is 6. So the greatest common factor is 6. So what does that mean? It tells us that that is the greatest possible number of designs in each row. There will be 6 cards in each row. The question was, how many rows will there be? Well, let's back up to the 24 special occasion cards. If there's 24 cards and there's going to be 6 in each row, how many rows of special occasion designs would there be? You simply take the 24 and you divide by the GCF, which happened to be 6. So there's going to be 4 rows of special occasion cards. For the birthday designs, there were 42, and we know that there's going to be 6 in each row. So again, we divide by the GCF, which is 6. So that's going to be 7. So to figure out the greatest number of designs in each row, how many rows of each group would there be altogether? There's 4 and 7. That would make 11 rows altogether. 4 of the special occasion and 7 of the birthday designs. So you're finding the greatest common factor, and then you divide the number by the greatest common factor. Here's another example. This happens to be on your worksheet, but it works the same way. Eloise saved all of her awards from school. She has 18 athletic awards, 27 academic awards. She wants to display the two types separately, but in rows of equal length. Determine the greatest number of awards she can put in each row, greatest common factor. So we have the numbers 18 and 27. Maybe you can look at those two numbers and determine what the greatest common factor would be. If not, if we used our method, we would find out that the prime factorization for 18 would be 2 times 3 times 3. And for 27, it would be 3 times 3 times 3. So they share 3 times 3. So the greatest common factor was 9, if you couldn't do that mentally. There. So how many awards are being displayed? Well, all of the awards are being displayed, but they would be displayed in 9 rows. And then how many, determine the total number of rows. I said that incorrectly. There's 9 in each row. Pardon me. Now, to figure out the total number of rows, we have to figure out how many rows there are of each. So if there are 18 athletic awards and there's 9 in each row, again, we take the 18 and we divide by the GCF, which was 9. So there's going to be 2 rows of athletic awards. There are 27 academic awards. There's 9 in each row, so we divide by the GCF, and we would find out that there's 3 rows of academic awards. So the total number of rows would simply be 5 because you add those two together. So in these scenarios, you always look for the greatest common factor, and then you have to, of course, read it and ask yourself, what is it asking me to find? But many times you have to go back and divide the number by the greatest common factor in order to find out the number of rows. That's a pretty long lesson. I hope it helps you today, and we'll talk later.